about how it might be interesting to introduce a concept of scaling into an axiom system of quantum field theory. It gives you then certain advantages, which I was trying to put up. But one of the things I'd like to say before leaving that, scaling is something that, if you look at any physics book, seems to be ubiquitous, how things behave when you pull the lengths in and out. But in the more abstract mathematical models of quantum field theory, it very much doesn't play a role. For example, I started off thinking about two-dimensional conformal field theories. And one of the first things that I was, so to speak, trying to model was what was called T-duality. For example, if you make the two-dimensional... Do I have any chalk?
Seems to have disappeared.
Somebody stole the chalk.
Well, if you introduce
One more.
if you introduce if you consider mapping Riemann surfaces into a torus, this is a standard compact real torus, then you get a sigma model, which is a conformal field theory in 2 dimensions. And it's well known that if you replace this by Langland's dual torus, that means you take the dual of the tangent vector space of this and divide by the dual lattice. Then you and consider maps of sigma into this. These two theories are identical. That's something called, I think, T-duality. And one of the first things I wanted to understand was why these were precisely the same two-dimensional conformal field theory. On the other hand, of course, this is totally incompatible with scaling, this isomorphism, because this changes what happens at short distances with what happens at long distances. And of course, if you have a non-conformal field theory where the long distance behavior doesn't interact with the short distance behavior, well, that's not the way this is. If we consider this abstract field theory, then it will occupy, in the sense that we had in Ibu's talk yesterday, very different points in his moduli space. In the short distance behavior, you model it in one region by this model, and in another region by that model, if you're going to take the scaling into account. The isomorphism between these theories is totally incompatible with the scaling. That's what I wanted to say about that. I just wanted to get clear, because one might think this is a property we just want to introduce into our models. We certainly want to know what we're doing if we're doing that, because we're making a big change. Well, the next thing I wanted to say something about, which should have been the subject of my third lecture if I'd been on the course, was about the question of locality. Supposing we have a theory which associates a vector space EM to a D-1 dimensional manifold. So you think of this M here, not the way I've usually been writing things, as a hyperplane section of some space-time. So this is a spatial slice in our theory. And so we associate to some topological vector space with states or whatever to that. Now, the thing that's obviously wrong or inadequate about the notion of abstract field theory that I was pushing is that it's sort of obvious that this really only models anything that's at all interesting if in some way this is locally constructed from this. In other words, if we were to write M as the intersection, the union of two pieces, M1 and M2, intersecting, let's call it sigma, in some codimension 2 thing like this. So we have our M, slice it by sigma, into M1 and M2. Well, wouldn't it be nice if we could just say, for example, that that we could tensor them together, and that will be isomorphic. Well, you see, nothing like that is ever true. In fact, it's, as it were, quite the opposite of being true. And the thing that was one of the first things I was very aware of and puzzled by when I started thinking about this subject, because I came into it through the representation theory of loop groups. And supposing M is a circle, and supposing and we're considering the theory, which the conformal field theory or whatever it is, which is got by looking at representations of the maps, the group of maps of this into a compactly group G. So we're looking at the loop group of G, which is the maps of S1 into G. Then EM will be typically an irreducible representation on G. Now, these representations have the following wonderful property. That, supposing you take the circle, well, in fact, it's perhaps a little bit simpler if we take, supposing we think this is like a line and spread it out interval, we could consider what I'll call L0 G, which is the maps of an interval into G, which vanish smoothly or break the identity smoothly at the ends of an interval. Then the representation theory of this group is exactly the same as the representation theory of this group for the class of positive energy representations we're talking about. In other words, any representation of this in the right class automatically extends to a thing where you don't put this condition at the boundary, but insist that the things are joined up. Well, on the other hand, supposing we now take a little tiny interval in here and consider, so let's call, so this, here we have our complete interval I, and we have a little tiny interval in here, I prime. And then we can consider, I should have called that, well, I should have considered, I called this thing Li B, and then we similarly have Li dash to be contained in that. Well, the thing is, this if we take any two intervals, so supposing I take I prime and I double prime, which is a much bigger thing, which contains everything except a little bit near the ends. Then we also have these intervals might be one much bigger and one containing the other, or I might have taken a second interval that was completely disjoint and a long way away. And the thing you know about the representations of loop groups of the type I'm considering is that they admit an intertwining action of the diffeomorphisms of the circle. So whenever you have one of these representations, there's automatically an action of the group of diffeomorphisms of the circle, which intertwines in a natural way with this action. So if we can certainly find a diffeomorphism of the circle which takes any subinterval I prime to any other subinterval I double prime, or which might be another little tiny interval over here, or it might be almost the whole thing with just a tiny little bit left out. Then if you restrict the representation to any one of these groups, then it's equivalent to what you get from any other interval. And the group of things supported in any tiny little interval will take any vector in the original representation, and its orbit will generate a dense subspace of the vector space. So you see, if you simply take the representation associated to this thing, which you think of with M up there, and think of this as being M1, then when you restrict to M1, this space is just essentially the whole space. So it certainly looks as if there's no possible way you could reconstruct, you could do anything remotely like that, you see. It seems completely incompatible with having an intertwining action of the diffeomorphisms of the circle. Nevertheless, the amazing thing is that that is not the case. This is local, and it's perhaps, you perhaps see the full, well, let me say it in general terms, it might be a little bit more convincing, because you won't realize quite, you can say it in such a way that it doesn't seem nearly so surprising as it really is. As you see how really surprising it is in the loop group case. What is true is that if you take, we're going back to M1 and M2, separated by sigma. And the following is true. The space associated to this total M is completely described as, for the purposes of quantum field theory, by giving the action on EM of all the smeared operators you can make out of fields over the whole manifold. On the other hand, if you look at the ones that just come from half of it, well, of course, they, if you apply it to some vacuum vector or something, give you a dense subspace of the whole space. But what you can do is consider, well, another thing that's true is if you just consider the algebra generated by fields in here and fields in here, supposing we call that AM1 and AM2, then these two things commute because these are space-like separated. So we would have an action of this tensor product algebra. And if you know this action on here, that is enough to determine for you the action of all the operators. In other words, that's the locality, the fact that operators are located at various places. And if you just leave out the ones that actually sit on sigma, it doesn't really matter. You've still got enough information to describe the system completely. On the other hand, if we just give this with that action, this with that action, it's not clear where we can go for the same reason as with loops. But what is true is that if you look at it, put a little collar around this, so that you have M1 plus and M2 plus. So M1 plus is M1 enlarged so that it goes a little bit past sigma, and M2 plus is this enlarged so that it goes a little bit past it that way. Then what you can do is, if you consider the field theory associated with these two slightly overlapping bits, and keep track of the action of what happens to things just on each side of the cut, then using that, you can reconstruct the whole representation. And the reason is a thing which is, to me, very interesting. So supposing we look at, so we have, let's say, the algebra of operators in M1. We say that that acts on EM. Well, we can look at the commuting algebra. So supposing we look at M1, the commutant. So all the operators in here which commute with all these things. Now, if you really take all those operators, it will be a von Neumann algebra. It certainly contains both AM2. But it also contains this much smaller thing, AM1 plus. And if you started with M1, you could think of lots and lots of ways of just prolonging your manifold a bit past the boundary. Now, the big theorem about the Tomita-Takasaki theorem about von Neumann algebras tells you that although this algebra and this algebra are very, very different, if you take their von Neumann closure, they're both, in both cases, you get the commutant of this. In other words, this is a very strange thing, which I think philosophically is very important in quantum field theory. If you just know about a little piece of the universe, and you can do experiments with all kinds of operators in there, and that will act on some huge Hilbert space of the universe. Well, you may ask yourself, what is it that you're not seeing about the world? There are all these fascinating operators outside the region you can study, and you have no way of knowing what they will do. On the other hand, if you were just prepared to say, well, let's look at all the algebra of operators out there. If we're prepared to think of it as a von Neumann algebra, we know it completely because it's well, sorry. I left out the theorem in that. The Tomita-Takasaki theorem says that if we consider the commutant of this thing, there's an anti-isomorphic, well, there's first of all a map, let's call it J, which is an anti-involution, which takes this algebra into this von Neumann algebra and makes this the von Neumann completion of, after changing the order of multiplication, makes this the von Neumann closure of that. So you see, first of all, that's meant to tell you that knowing the von Neumann algebra is really not really knowing anything at all. So that's the first thing. If you just want to know the von Neumann algebra that acts beyond the horizon, you know it already because it's completely determined by the operators you have in your hands. That, in fact, I want to emphasize, doesn't tell you anything about what's really happening outside. But it tells you enough to reassemble these things. So if you take the if we take the operators in this slightly enlarged version of M1 and think of them as representations of the von Neumann algebra of things that just sit in that little tiny strip. So the commutant of the action of M1 in this slightly larger thing. So you think of it not just as a vector space, but as a representation of the algebra of operators in here. And you only need that as a von Neumann algebra. Similarly here, you have this thing, and you look at it as an action of whatever's there. And both of those things are things you can work out just from this bit of the data. Then that gives you enough information to reassemble the actual global situation. Having those two von Neumann modules, we can reassemble a vector space in such a way that this and this act on it. And these things how the operator, they generate the operators everywhere. So then we have the whole picture back. So it's very, very surprising fact about the way you put things together. And of course, what it does is it tells you how to extend your theory, assuming you can do this rather generally. It tells you how to define the it tells you how it tells you what we need to associate to a codimension one, a codimension two manifold, so as to be able to extend our theory one dimension down. So let me just try and explain it. Go back to loop groups and where it's maybe a little bit clearer what one is doing. So we have an interval, and we're looking at maps of this into some group. We have the interval cut into two. Now, here is our left-hand half. And what we're going to do is consider all possible ways of extending this coupling. It doesn't have to be, this will be one of them, but you can consider any way at all. There'll be an algebra of loops supported on any one of these things, including this. And we know that the representations of the loops supported by any one of these bits, they all look the same because of this property of diffeomorphism invariance, which tells us that we can think of this picture as the way I've done it as happening in the we're in a two-dimensional manifold, because this is part of a two-dimensional field theory in which this is our spatial slice, which we're cutting into two with this thing of codimension two. Well, whenever we have a possible cobordism like this, which is actually a cobordism between that and that, we get an operator in our theory from what we associate to that to what we associate to that. And so that takes the algebra of the loops based on that, the loops based on that, so to speak. And then we can take it to the loops based on this, loops based on this, and so on. Well, so what you have to do is consider this with a little bit of an extension. Think of it as going up like that. And consider this with a little bit of extension, say going down to there. Supposing we give the representation of this with know how loop space there act, and this, and we know how loop space there act. We want to reassemble the whole thing. What we have to know is how to relate representations of that bit with representations of that bit. So we need an isomorphism between these different ways of extending the half space. So we need to know, not quite, I was exaggerating when I said we need to know, well, we need to know the representation of the Neumann algebra is associated to the two little flaps, but we also need to know how they relate to each other. And they are related to each other by the bimodule, which we get by thinking of the little flap as a space-time in its own right. And seeing that it's got an action of this on it and an action of this on it. And you can think of that bimodule then as a generalized transformation from representations of this to representations of this. So in fact, what the upshot is the following thing. What we have to associate to the thing of codimension 2 is first of all an algebra for each little extension of M1. We consider all the possible little flaps we could put on. And we then have to have a bimodule which relates representations of this, the algebra based there, the algebra based there, corresponding to going like that. And in the trade, this is called the Tomita-Takasaki flow, and it's an action of, actually an action of C multiplicative on the, it's usually, you can identify all these flaps with each other if you want to, and think of it as an action of a single von Neumann algebra with an action of C multiplicative. And that's called the Tomita-Takasaki flow. It's usually considered in the functional analysis literature along the real axis, in which case it's simply rescaling it along any single flap. I'm doing a Wick rotation so that I'm pushing it from one flap to the next flap as we go round. It doesn't close up though when you go around 360 degrees, because once we do the Wick rotation, these will, so to speak, be extremely non-isomorphic things. The flow would be unitary if we simply rescaled in and out on a single flap, but it will be, as it were, conjugation by a, well, it'll be something that you have to represent by a bimodule. It's like trying to conjugate by a non-invertible element of the group when you go this way around, in the same way that a unitary operator becomes a contraction operator when Wick rotated. So anyway, you can certainly consider the category. It's actually not a very difficult category, particularly in the case of a loop group. It's essentially just the complexification of the action of diff S1 on all the little flaps around the point. Well, I took too long to say that, and perhaps didn't say it so brilliantly. I think
in a topological setting, simpler setting, topological, you would have, to codimension 2, you would have a category, linear category attached. Or the state spaces would fail in the same way that you said. You would take what's called a coend over the category, so you sort of sum up all the connections.
well,
Is that related to what you're doing?
I think if it's really a topological theory, this will become trivial because all of those bimodules will just be representing the identity map. You see, we don't have any propagation. So, yeah, I think you see in the topological case, there's no reason not to think you just have a linear category, and that's that. You don't have to have a linear category which is really got this action on it. Yes.
Can I ask another question? Do these bimodules need to be invertible? So can you go from one flap to the other and then back again?
No. It's got a time direction. It's like a kind of, it's like when you rotate a propagation in Lorentzian space-time to complex time, then you can only go in one direction. You can't go back again. It definitely becomes a contraction operator. So it won't be an invertible bimodule.
So it doesn't give you a Morita context between all of these algebras.
So when you go right round, it doesn't close up after 360 degrees. It's yes, it was wrong of me to call it an action of C multiplicative. It's an action of the universal covering of C multiplicative, really. It's well known. This is well known to people who do general relativity, because they sorry, I have a senile moment when you have this picture in general relativity where you have a codimension in Minkowski space, you have a codimension 2 space, and you consider the famous diagram, the light cone, and people talk about the something wedges. Anyone remind me what that word is? Well, it's well known that
Causal?
sorry?
Is it causal?
Hmm?
Causal? No.
No, there's a mathematician with an Italian name in that.
Euler?
These are called the something wedges, or in all relativity.
Rindler, man.
Hmm?
Rindler.
Right.
Are you talking about the Rindler space-time or?
Yes, Rindler isn't the person, but they're called Rindler wedges, but actually he isn't the right. What I wanted to say was that this flow in this situation, when you consider field theories based here, is known when you do it radially to be the action of Poincare boosts in and out along the trajectories of the Poincare group in that picture. And you see what the Poincare group does is simply rescale the metric in that direction. And that's of course what I said this flow did here. So this is something that's actually very well known in ordinary special relativity, in fact. Anyway, I think I've said enough about that unless someone else wants to ask more questions. I'm sorry, I didn't say that last bit very well. Let me change subject. So this was where I now want to tell you about my misgivings about the fact that quantum field theories take their, if you think of them as cobordism functors, into some linear category. This is, we're really going into some non-commutative geometry category. And what do I mean by that? Well, well, the thing that you see, when you supposing you have a non-commutative ring, algebra over C. Supposing, first of all, supposing we had a commutative ring, so something like the C infinity functions on a manifold M, then we know that from this we can reconstruct the geometry of M completely just by finding the points of M as the homomorphisms from this algebra into the complex numbers. In other words, we can reconstruct all the geometry just by looking at the category of modules for this commutative algebra. Supposing we have a non-commutative algebra, when you study its category of modules, a non-commutative geometry is always about the category of modules. It's never about the actual algebra. So, for instance, if we replace the algebra by an algebra which is Morita equivalent, that's one by definition which has the same category of modules, then it's universally agreed that that is not changing the non-commutative geometry. The thing that has the geometry is the category of module. Well, you know, of course, that you can look at, for instance, define K-theory of an algebra by looking at the finitely generated projective modules. And you can think of that as the homotopy groups of some space. And people often think, well, that tells you all about the space, because, for instance, we know that in this case, this is isomorphic, at least if we tensor it with the rationals, just to take the simplest case, this would be the sum of the rational cohomology groups. And so this is very like knowing about a space. because it, uh, this tells you a lot about what the space looks like, but that's extremely misleading. How did we do this decomposition? Well, we did the decomposition by saying we can do this decomposition, of course, only when we have something commutative here. Because when we have a commutative algebra, we have Adams operations which act on this. And these things are the eigenspaces, this is the decomposition into eigenspaces of the Adams operations. Now, the Adams operations, what do they come from? They come from taking a representation of E and, in fact, looking actually at its successive tensor powers together with their actions of the symmetric group. When we study that, we look at this will give us the Adams operations, and that will break it up. So in particular, we're considering things like the exterior powers of E and things like that. Well, on the other hand, that is something you absolutely can't do except for a commutative. These are operations you can perform if and only if essentially the algebra is commutative. So we have nothing like Adams operations for a general ring. And it's actually rather important, you see, that I want to draw attention to this scaling because the fact that we're using several properties of it. We're using the fact that we can decompose these in order to get this decomposition. We're using the fact that we can decompose this according to the symmetric group. Now, for instance, if we were doing a corresponding thing with, let's say, complex cobordism, a different cohomology theory, then a similar thing would be true, but more complicated, because instead of getting Adams operations, which are just essentially an action of the multiplicative group of the rationals on the K-theory, you would get an action of some formal group, which involved the formal group law of the theory, and it would be not an action where you could divide, it wouldn't give you a grading at all, it would give you something very much more complicated, and that's the subject of chromatic homotopy theory. And you see, it always struck me that one of the things you really can do in quantum field theory is tensor vector spaces with each other, and that's an exactly symmetric operation. You don't have formal group laws coming in and so on. And so just as when you go from the category of spaces to the K-theory category in algebraic topology by taking this functor, you lose most of the interesting higher integrality properties of the proper homotopy category and replace it by much cruder ones. You certainly aren't going to, even if you somehow could get back to having this decomposition, then you will, I suspect, never be able to find all of this subtle higher homotopy from things that you can get out of the ordinary homotopy category. That's just a speculation, but I think it's quite an interesting speculation. As to the existence of this operation, well, you see, it's definitely to do with the fact that we can grade things and this kind of scaling I'm talking about, which essentially says that you're really close to a commutative ring, precisely provides the possibility of doing this in, so that's the significant going between the possibility of making some decomposition like this on the homotopy level is exactly what the scaling is doing. Exactly the kind of thing wouldn't be preserved by T duality. So there's another general remark I'd like to make about the homotopy category. Sorry, about the non-commutative homotopy category. The most important thing about it is that it has got periodicity. That's the following fact. If you think of the category of modules for C infinity, let's say R2, and I'll make it, I'll consider things which decay rapidly at infinity, the Schwartz space, smooth functions like that. Then this is, you can think of this as the operators on a two-dimensional dynamical system where here we have, think of these coordinates as being something like position and velocity of something moving in one dimension. Well, this has a canonical quantum deformation, the natural Heisenberg deformation, in which you, the functions on the two axes, you make no longer commute, but have a scalar commutation relation. The commutant of multiplying by the coordinate on one axis and the other axis will be I or something, I times Planck's constant. Well, of course, the coordinate functions don't decay at infinity, but there's a quantum deformation of this, which does exactly that process, the standard quantum deformation. And when you do that, and consider this deformation, I'll put an H there to make for Planck's constant to make the deformation. And this is no longer a commutative algebra, but it's on the nose isomorphous. The smoothing operators, and this is just a matter of Fourier transformation. This algebra for any non-zero value of H is isomorphic to the smoothing operators from C infinity R infinity R. You can think of this as the quantum space. And the smoothing operator is just one which takes a function f to the function kf, where kf is x and y. Where this is a smooth function of two variables, that will be the function we have here. When we write it like this in the non-commutative thing, the composition of smoothing operators is exactly what you're going to get. That's a remarkable fact that's true on the nose and just involves simple Fourier transformation. So this is essentially a full matrix algebra, these smoothing operators. It only has one irreducible representation, which is the natural one on the smoothing operator, on these algebras of functions. So this is Morita equivalent, has exactly the same category of modules as the complex numbers. So therefore, if we are going to have any kind of theory which is going to allow any kind of even the tiniest quantum deformation, then these two objects are the same. Now, this is the algebra corresponding to R2, obviously. So more generally, we're going to find that if we have any object of the non-commutative homotopy category, it's going to be homotopy equivalent to x cross R2 compactified, as it were. In other words, the double suspension of place. And that corresponds exactly to the fact that you can't single out dimension. You see, here we have this Bott periodicity, which shifts things by 2 dimensions. In the non-commutative homotopy category, we lose the concept of dimension. Now we can maybe possibly try to put it back by these scaling methods that I taught. But if we don't have them, we're certainly hitting this object problem immediately. And in fact, what do the objects of this category look like? Well, you see, the fact that this is the essential difference between the two categories. The fact that you've imposed this Bott periodicity because of a fundamental fact of quantization. And it means that whereas we can make objects of the homotopy category by taking compact things and putting one in another and so on, and making bigger and bigger spaces. We can make objects of the CW complexes by pinning pinning together cells one after the other. When we do the corresponding non-commutative thing, we start off with perfectly simple objects which maybe look like a space, but when you want to make them a bit bigger, you can't just, what you have to allow is the fact that these things might shift dimension by suspending any even number of dimensions. So what we get for the typical non-commutative objects is limits where things can be, as it were, desuspended as you go along. And of course, they're precisely the objects of Floer theory. You see, what you get is naturally Floer homotopy types, not just ordinary homotopy types. Well, it would take a lot to say anything very much about that. So I'll go back to, I'll just say, I said that my basic aim in looking at quantum field theory in the way that I did was that I was interested in trying to get some idea of what should be the right model of space. I mean, we certainly arrange all our perceptions in space. We can only interpret things in terms of putting them in space. So what should be our model of space? And I'd like to just point out the conjecture for that. I wanted to talk about what I call the smooth homotopy category. There are many slightly different versions of this. Well, if we introduce some kind of scaling axioms and things like that, so that we can make our theories seem a bit more like space, what kind of things do we really see when we do quantum field theory? Well, as Ibu said in his lecture, the main thing we have is the long distance behavior, which sort of looks rather like homotopy theory. We don't have any more a notion of distance. Things can be shoved around. All we have is global homotopic kind of structure. On the other hand, so you might think, well, so at one end, we're looking at objects which have some kind of homotopy theory. On the other hand, we can also look at short distances. Now, I think quantum field theory in its approximations is very much about manifolds. Now, of course, not everyone thinks this. People who work with lattices and consider some kind of way of making points of a lattice interact and then let the lattice spacing tend to zero, they are potentially looking at things with really quite potentially weird local behavior. But I think that physics somehow is kinder to us than that. And what we see when we look at things at short distances is a manifold, and a smooth manifold at that. Now, why do I think that? Well, you see, I don't really think it's God being kind to us. I think it's because we are creatures who have a way of looking at the world the way that we want. And how do we look at things close up? Well, we introduce a coordinate system. In other words, we just look for things that can be set out in something like Euclidean space. I mean, we don't see too much detail, just the same way as we don't see things that are moving very fast. So I think we put in the notion of manifold. And what is the notion of manifold? It's saying in terms of the ring of functions that when we look close up, what we have is something like a formal power series ring in independent variables. that locally, that's what our spaces have to look like. Well, is there a category of objects like this? Well, there certainly is, and it's been much studied for a very long time in many different in many different situations. I got interested in it long ago when working with Raoul Bott on the cohomology of vector fields on a manifold, with Gelfand-Fuchs cohomology, so-called. We proved a theorem which said that the cohomology of this Lie algebra looked like the cohomology of some space. And immediately one thought, well, how does a Lie algebra manage to look like a space? And of course, once you ask that question, you realize you've been sort of doing that all the time, because we look at cohomology of finite dimensional Lie algebras, and sometimes, say for a compact group, it looks like the cohomology of the compact group. If you look at, say, the Heisenberg group, and it doesn't seem to have any topology at all, but you still have cohomology groups for the Lie algebra, and so on and so on. Well, what are these homotopy groups? Well, what people realized long ago, but there are now very many much better technologies for looking at it, is, well, remember that the homotopy category, if you just want to consider it like an old-fashioned homotopy theorist, can be regarded as the contravariant functors from, say, finite CW complexes, compact spaces, perhaps. The sets, contravariant functors like that, which have a certain sort of Meyer-Vietoris property. Then there's a famous theorem of, I'm sure, 7 homotopy classes of maps. If we consider functors like this, with a certain Meyer-Vietoris property, they correspond pretty much exactly to homotopy types. That's a theorem of Ed Brown long ago. Well, to make the smooth homotopy category, you keep this exactly the same, but you replace the category of sets by the category of smooth manifold. And then you get a beautiful category. And in many ways, we know there are now better ways of saying this, because we now understand, because of the theory of, well, we understand abstract homotopy theory a lot better now, and we understand that you have to introduce Quillen's. You never really want to consider a homotopy category literally. You want to consider a larger category of objects and make a homotopy category out of that. We're not going to go down that road in the remaining 2 minutes. I just want to give you some examples of this. This is something that was pointed out to me many, many years ago by Quillen in the 1960s. So supposing we have a Lie algebra G. Well, first of all, this category is equivalent. Let's change it a little bit. We don't absolutely need to, but let's change it a little bit. We can equally well say finite dimensional smooth manifolds, open manifolds, and smooth maps between them, up to smooth homotopy. That's exactly the same category as this. So supposing we take a Lie algebra G, and then to any object of this category, we associate the flat G connections up to isomorphism. Now, we have to be a little bit careful when I say up to isomorphism. You see, the flat G connections are certainly a manifold. They're the one forms which obey obvious curvature condition. And we're introducing an equivalence relation. So you have to be a little bit careful what you have to be rather liberal about what kind of smooth manifolds you allow there, so that you allow yourself to put in quotient structures that are inappropriate. So this certainly is such a functor. And that is the homotopy, that's the homotopy type of the Lie algebra. That is the Lie algebra as an element of this. And for example, we know that we could consider flat G bundles. If this is a Lie algebra of G. Exactly, this would be another object of the category. And this would be the thing that gives you the smooth homotopy theory of the group G. That's the thing which was determined by Hochschild a long time ago. It's calculated by Hochschild from the Lie algebra cohomology, because there's an obvious map in that direction where you simply take from the bundle, you just consider the associated bundle of Lie algebras.
Excuse me, sorry. Could I ask one question?
Sorry?
Could I ask a quick question? You're defining a smooth homotopy.
Sorry, I realized I just said something a little bit wrong. I meant it in the trivial bundle in this case. So I not only wanted to be a flat connection, but I wanted to be a flat connection in the trivial bundle.
Right. But this is a definition of a smooth homotopy type, is that
This is a particular smooth homotopy type, and I claim that's the smooth homotopy type of the Lie algebra. This is the this would give us another smooth homotopy type, which is well known in the theory of cohomology of topological groups, and so on. And this way you can interpret give a homotopy type to a Lie algebra of vector fields. And better still, there's a really beautiful paper of Kapranov where he does this. One object in this category, which I don't have time to explain now, is you can take the base loop space of any manifold you like, based at a certain point. And this can be precisely exhibited as an object of this category. And you can see that if you look at it, it has a Lie algebra, which is precisely all. If we are looking at a manifold, but supposing we looked at the base loops on a Riemannian manifold, then we can make. So supposing the Riemannian manifold was X, we're looking at some base loops in X at some point. This is an object of this category. I don't have time to explain it properly now. Kapranov in this picture calculated the algebra, and he observed that he observed first of all that if you have any bundle with connection on X, it will give with structure group G, it will give you a homomorphism in this category into the Lie group G itself, regarded as an object of the smooth category. And he observed that there's an induced map of Lie algebras in this category, which is exactly all the curvature data that you can get from the Riemannian structure. And on the other hand, the long distance behavior completely records all the homotopy data, because well, we know that the homotopy classes of homomorphisms like this give you the classifying map of the bundle. So I'll just finish then with one sentence. I'm sorry, I've got a bit over time. You see, this category you can look at in the following way. The homotopy category is somehow made from the category of sets in the following way. You start off with sets and you say, well, suppose you allow yourself to have power to add the concept of a path going from one point to another. And then you allow yourself to add the concept of a homotopy going from one path to another. Then go up homotopies between homotopies and so on. so we make the homotopy category as a series of refinements or extensions of the category of sets, where we allow ourselves to do successively higher homotopies. You see, homotopy theory is a fundamentally perturbative theory. You do it one homotopy group at a time, and that's why you can do algebraic topology, because you do it one step at a time. Now, analysis, the theory that we do with differential calculus, we also work perturbatively. We start with we start with, if we have a function and we want to study it near a point, we first look at its value, and then we look at its first derivatives, its second derivatives, its third derivatives, and so on. So we have this filtration by order of number of times differentiated. So it's also a fundamentally perturbative theory, where the perturbation is getting, as it were, it's going in the opposite direction to the homotopy perturbation. Now, if you actually started with the category of sets and do the upward step, we get the honest homotopy category. In this category, this smooth homotopy category, we have the wonderful property of being able to do perturbation theory in both directions. We can do it homotopically upwards, or we can do it by looking at successive curvatures and things infinitesimally. So just as quantum field theory is done perturbatively, however we look at it, it's done perturbatively, and we have a sort of long distance perturbation theory and a short distance perturbation theory. That's exactly what you have, I claim, in this smooth category, smooth homotopy category. Well, I think it's more than time for me to stop.